So Dan, maybe to start, we can talk about how you got into astronomy.
Oh, that's a good question. So I remember sitting around in the library at my elementary school reading all the space books, so I was always interested in it. That's too unusual. Eventually, I got my first job at a drugstore, and instead of buying a car or something like that, I bought a telescope. And I also always liked to build things, so when I got to college I started looking for a summer job where I could work on an astronomy experiment. And I found myself working on the cosmic microwave background. There's a lot of interesting stuff going on at the end of the 90s on the cosmic microwave background. People were just being able to measure fluctuations in this. And so there were a lot of experiments being developed. And so I joined to one of those, and that led me to a career in video instrumentation and
So maybe let's start with the microwave background. Area precision of the measurements being done is sort of amazing to people who knew what they looked like a few decades ago. So maybe you could sort of paint a picture for what the current state of the art of CM is.
Well, so when I started in this work, my first CMB experiment work was 1997, and it was just at the time, the best measurements of the CMB when I started in 1997 were from the COBE satellite. And COBE won a Nobel Prize for, among other things, being the first experiment satellite to measure any deviation in the temperature of the cosmic microwave background across the sky. We knew it was very uniform. It was predicted to be very uniform from cosmological theory, from inflation. But people really wanted to see the changes in it because ultimately the temperature differences in the cosmic microwave background are what collapsed into the structures that are the universe today. So in 1997 with COBE we had measurements of fluctuations on very large scales, 7-degree scales. But what people really wanted to know was what was the angular scale with the strongest fluctuation. And
then just as a sidebar, talk about how subtle these fluctuations are. And also, it was kind of interesting with COBE how it was just on the hairy edge of detection anyway in terms of the prediction.
Yeah, so the CMB was discovered in the 60s, and people spent years looking for fluctuations in it because the actual fluctuations are a part in, a few parts in 100,000. So it's a very faint signal in the sky. The temperature of the sky is 3 degrees above absolute zero, and you're looking for very tiny fluctuations in this 3-degree signal. So anyway, the COBE measurements on the 7-degree scales were, this was the biggest. This was the angular resolution of the telescope they could fly, but 7 degrees wasn't exactly the size you wanted to look on. There's not much fluctuation on 7-degree scales. If you could get to about a degree, everyone expected that there would be much stronger fluctuations. But this was the scale, this was basically the size of a patch in the universe where light could travel across it at the time the CMB was released. So the universe had been expanding, and light can only get so far in the entire history of the universe. So this is the size over which temperature can equilibrate. People wanted to see the fluctuations on that size because that's where the dominant fluctuation should be, the size where light had time to communicate the temperature.
So this is finding fluctuations that had their power on the scale you expect is a pretty sophisticated test of the Big Bang model anyway.
That's right. We think we know now, especially we know that the physics of the universe at the time of cosmic microwave background are simple, relatively speaking. We can write down, generate on computer very quickly, simulated universes, and it's just a bunch of matter, ionized matter in gravitational potential that's created by the dark matter that also is in the universe. And with just these two components and physics that you learn in college, more or less, you can predict what the distribution of fluctuation should be on scales of on these acoustic scales. So the oscillations within the volume boy, I'm getting myself down a hole here. How old are these people who I'm talking to?
All ages. All ages.
Okay. Yeah, well, I hope you have a lot of physics. Okay, so in any case, with relatively simple physics, you can calculate how the temperature fluctuations should vary with linear size.
Mm-hmm.
We know roughly how far away this surface is. This cosmological background was released from. That's part of the cosmological measurement, is getting exactly that distance, because we know roughly the size of these fluctuations. And so you can convert this linear size to an angle, and then we can look for this angle on the sky and measure the geometry of the universe between us and that surface. This was the big measurement that was trying to be done when I started in this field. So we had almost no measurements of these fluctuations. Kobe had just barely measured any change in temperature across the CMB. They'd gotten a Nobel Prize for it, although at the time they hadn't. That was much more recent.
And Fingerprints of God had newspaper headlines at the time, of course.
Yes. I don't quite remember that, because I think when the Kobe results came out I was in junior high, but yeah. And so then these new experiments were much more sensitive, and they went up on balloons, and they mapped tens of degrees of sky, and they found these fluctuations exactly on Drie's scale, and it was very exciting. It said that the universe was flat, which meant that there's basically a perfect balance between, in the cosmology of the time, or the cosmology that I had grown up with, and I think we all had until we started accepting the idea that there was a cosmological constant. But the universe was flat. It was supposed to be the universe that would expand forever, stop expanding just at infinity. It meant that angles, if you could draw a triangle between us and the cosmological background, that the three angles in the triangle would add up to 180 degrees, as opposed to a universe that was, say, open, where it's like drawing a triangle on a saddle, so the three angles will add up to less than 180 degrees, or on the surface of a globe, which is a closed universe, where they would add up to more than 180 degrees. So measuring that the universe was flat was a huge step forward. But people could just barely do this. These peaks in the CMB, even then, well, I guess in the first two measurements, they were pretty good. Signal noise of several on the measurement of this first peak, the most prominent fluctuation in the cosmic background. But now we've gone a lot further. So in the time I've been working in this field, starting from when I was 18, I guess, we've now gotten to the point where instead of just measuring one peak in cosmic background spectrum, we've measured about 11 with a Hubble telescope.
Wow.
And you can actually see the fall off in the fluctuations as you get to finer and finer scales. And the physics of this are relatively simple. It's just the diffusion of photons in the plasma of the early universe. But it was
and these are like literally harmonic, so this is some echo of Kepler's harmony of the spheres written into the universe.
That is a great way to put it. Yeah. So these are the the fundamental mode in the CMB is the sort of degree scale fluctuation, but on top of that we have these weaker and weaker harmonics, and they get weaker as you get further out, and theory predicted how this should happen, and now this has been measured. One of the big results from the Planck satellite, which just released its results last month, March? No, we're in May now. So in March, was that not only do these fluctuations fall off as you get to higher and higher harmonics, but they fall off a little bit more than you'd expect if the initial spectrum of fluctuations in the universe were a simple scale-free, we call it, spectrum. So there's a little bit of a tilt to the spectrum of the fluctuations in the early universe. So the harmonics are not as pure as we expected, but they on their own fall off. And this imprint is seen in the CMB spectrum now that we can measure not just one peak but 11.
And what are these details? I mean, people may wonder as we keep getting better and better data on the CMB, what questions are we still trying to answer? I mean, Big Bang model, okay, that's nailed, but what are the frontier questions now that motivate even finer measurements?
Well, it's funny. So the Planck results really, I mean, absolutely have nailed the spectrum of temperature fluctuations in the cosmic wave background. So but there were surprises even in that. So we thought we pretty well had this nailed. By measuring these things, we get cosmological parameters out. Initially, we think these spectra could be described by basically 6 numbers. The amazing thing is that several of these numbers changed when Planck came out with its results. And as exciting as that is, it upset a lot of things. So we actually have a lot more work to do to figure out what just happened to us. I felt, when I got the first paper up on my screen, I was waiting for the release of the papers. I looked at the cosmological parameters, and 2 of them, the total amount of matter in the universe and the amplitude of the fluctuations on a certain scale, increased by a pretty significant amount. So there was more matter in the universe and there were more fluctuations. If you add more matter to the universe and you increase the amount of fluctuations, you expect that you should form a lot of structure. If you start with a very smooth universe or a universe with nothing in it, then obviously you don't grow a lot of structure. If you start with more matter or make bigger fluctuations in that matter, you will get more large structures. So the Planck results suggested that there ought to have been a lot of very big structures. And it turns out I've been looking for these structures for several years now. They're called clusters of galaxies. They're the biggest structures in the universe. And the idea is that the universe predicts, our model of the universe says it's going to take the entire history of the universe to form the largest structures. So if you can count how many there are, you can say with great precision, these 2 numbers, how much matter is there in the universe and how many fluctuations are there. So anyway, we've been looking for these galaxy clusters, we've been finding them, we've been counting them, we infer these 2 numbers. Planck changed these numbers, and in fact the Planck numbers predicted that there should be twice as many galaxy clusters as we actually observed. And so that was a surprise. Now, how do we fix this? The physics of all this is pretty simple. So, something could still be wrong in the measurement. It's very early days. More exciting things happen, though. We wanted to describe the universe with 6 numbers. Maybe now we start adding more numbers. So, for example, if you want to make structure form more slowly, you can add mass to neutrinos. Neutrinos are, were present in enormous numbers in the early universe and still are today. Because they don't pool up in the gravity of the dark matter potential wells in the early universe, they sort of smooth out the growth of structure. So you can add mass to neutrinos and fix this problem. It's one of the exciting possibilities of this. So by measuring
and this is without declaring them to be the dark matter in total, as a component.
Yeah, no, that's right. So they still wouldn't be, they still would not represent,
They're not going to hold the
they're not-
clusters together.
No, they're not switching to hot dark matter or anything like that, which is the relativistic particles being the dark matter, like neutrinos. This is just a little bit of a tweak to our model. Very little mass to these neutrinos, but enough to smooth things out. And so these sorts of changes to our physics are where we stand now in CMB. But that's just looking at the temperature of the cosmic microwave background. You can look beyond that, and this is what people are trying to do now. Planck, as an experiment, started when I started in the CMB. So the science was driven by what we were thinking about in 1997 and 98. Mm-hmm. And so the polarization, the next step in measuring the cosmic microwave background, wasn't really a concern then. The polarization in the cosmic microwave background is a bit more complicated to understand, but the main thing to know about it, your listeners, viewers, students, what do you call them, will certainly have experience with polarization. You can look at I guess my favorite now is you can look sort of in the late afternoon or early morning, look 90 degrees away from the sun with polarized sunglasses on, and you can get the sky to be very dark depending on which way the polarization is oriented in your glasses. Tilt your head 90 degrees if this doesn't work. But that's because all the light that's coming to you from that blue sky is being scattered very strongly towards you. So it has a very specific polarization in that direction. In all other directions, it's more mixed. The same thing happens with the CMB. Photons come from hot regions of the CMB. They scatter off the gas, and it creates a polarization signature. The other source of polarization in the cosmic microwave background is gravitational waves in the very, very, very early universe. This polarization I described first is something that's effectively simple physics that you could calculate with college stuff. Mm-hmm. People have measured that. First measurement was in 2001 roughly by the DAISY experiment. So people have been doing that for a long time. But what people want to do is get past that measurement to this very weak signature that should be there from inflation, and get a look at the physics that were going on back when inflation was happening, back when the universe was expanding exponentially. And these gravitational wave signatures in the CMB are little tweaks to that polarization signature. So the next step over the next few years, and first results of this generation of experiments, you could say a couple have been published, but the first real results from this generation are coming out in the next couple of years, will be people trying to look at inflation using these little tiny deviations in the polarization. And looking at the time of inflation, it's not something we can normally do. We can't look at light that comes from the time of inflation, because the universe was entirely opaque from the time of the cosmic background before. It's like trying to look into the sun. We can only look for this time through inference, things like this polarization. So it's going to continue to be exciting, even though it's pretty mature.
And it's worth just dropping back and realizing how amazing it is to be testing the Big Bang, the mature Big Bang model at 10 to the minus 33 seconds after it, with real observations.
Yeah, well, yeah. So it's amazing, and it's a heck of a technical challenge. These signals are incredibly weak, and you have to have far better systematic control over everything you measure than we've ever achieved before. In fact, the leading experiments in this field are kind of hung up at the moment on getting to that
So we're talking about control. 1 part in 10 to the 7 here? What is the precision required for that, say, that inflation test?
So part in 10 to the 7, I mean, it varies a lot over angular scale, but sure, that's an okay number for the sort of largest scale fluctuations. Yeah, so it's a very tiny.
And since you work on instrumentation, let's talk a little bit about how we actually do measurements like that, because that level of precision in a non-terrestrial lab experiment is pretty impressive. So how do these satellites achieve anything like that level of precision? What are their methods?
Yeah, so let's take Planck for an example. So Planck has a bunch of different detectors, and basically all they're trying to do is in some frequency range, so pick a color in the sky, in the microwave sky, and measure the temperature of the sky in that frequency range. So how do you do this? Well, it turns out if you want to measure a very tiny change in temperature between one patch of sky and another, then you need a very cold detector that can absorb the light from that patch of sky and let its temperature go up or down. We call this a bolometer. Basically, you take a piece of semiconductor. In the case of Planck, things have gotten more advanced since, and you cool it to nearly absolute zero. So I think Planck was probably running at 70 or 100 milli-K, so thousandths of a degree above absolute zero. So these little tiny bolometers are sitting there. The telescope focuses the light of a patch of sky onto them, and their temperature changes by a very tiny amount. Through a careful electrical measurement scheme, basically the electronic system responds to the change in temperature by stabilizing it. You measure the power you need to input to stabilize the system, but they can measure these very tiny fluctuations, by sensing the change in current through one of these detectors.
And the key is that this is differential measurement that helps you be that precise.
That's right. So it would be very, very hard, although there are some experiments that have done it, including Kobe, to measure the absolute temperature of the CMB. It's a little bit easier to measure fluctuations between one patch of the sky and the other. So you scan over the sky and look for the changes. So that differential measurement is one piece of making this very fine measurement. Other pieces of the differential measurement are the actual readout scheme. So instead of keeping this is getting deep in the weeds now. You AC bias the bolometer. Let's not go into that. Right. But anyway, whenever you want to make a sensitive measurement, it turns out that the best thing to do is always to take a difference rather than trying to read an absolute number. And so there are multiple layers of differencing stacked on top of each other, differencing between sky, differencing the detectors with each other, and differencing the detector with itself. Anyway, through adding these things up in layers, people can get very precise measurements, and the polarization measurements are yet more layers of that, because then you difference polarizations, and you do even more sophisticated differences on the sky. But yeah, this is the only way you can get to these very small fractions.
And how critical in this is the stability of the space environment for making? I mean, this can't be done from the ground, presumably.
Yeah, so people have been doing pretty well from the ground, space makes things better, but space is extremely expensive, and so people started by doing this from the first really good measurements were from balloons, which is effectively space. But as the detector technology got better, and as it's mostly there's a big change in detector technology that made it a bit easier to do this from the ground. You can do it quickly from a balloon, or you can do it slowly from the ground, because you have more sky emission between you and the cosmic background on the ground. But the advantage of the ground is you can put a lot more detectors on the sky typically. And so yeah, the space environment is good, but for this next generation of experiments, people are doing things to prove it can be done, to get close, to justify the next investment in a space experiment, maybe 10 years away, a cosmic microwave background polarization experiment in space.
Right. And of course, another aside on the polarization measurement is it's a sort of indirect detection of gravity waves, which is still very hard for us to do directly. I mean, LIGO's upcoming, but we don't know if it's going to see early universe signatures.
Yeah, that's true. So in the intervening time, we've gotten closer in multiple ways to looking for these same sorts of signatures. Of course, both in cosmic microwave background polarization and in directly detecting gravitational wave noise from the early universe, we don't actually know how strong the signal should be.
Mm-hmm.
And so in the CMB game, the goal is always to push down the limit to how strong these gravitational wave signatures can be. It's a different frequency scale that's relevant to the direct measurements of gravitational wave noise from the early universe, but it'll face the same uncertainty.
And is the current state of play, is it fair to say the inflationary hypothesis has tentative support from the data so far?
Yeah, well, so, I mean, absolutely. Inflation...
Or is it stronger than that? Is it better than
Well,
that?
I mean, without inflation, there were mysteries of the universe we had no way to explain. How could that patch of sky in one direction match that patch of sky in a completely different direction when they've never talked to each other?
Right.
So, fundamentally, this picture has incredibly strong support just by the fact that it explains so much that didn't make sense about the universe. But in detail, we don't actually understand the physics of inflation really at all. And so another exciting thing coming out of the Planck measurements was a little bit more information about what the physics of inflation could possibly be. What could be the nominally you'd think this would be pretty simple physics that lead to the universe expanding exponentially for a time. There's almost an infinite number of models, though, that could do that, and some subset of the infinite number of models is excluded by what we've got from Planck already. But yeah, there's a long way to go in understanding what actually was going on there.
So let me get back to clusters for a minute. You've talked about one powerful way they're cosmological tools, just counting the abundance of them over cosmic time. Are there other ways that they're useful as tools in cosmology?
Well, so a newly interesting thing after Planck. Perhaps the longest term cosmological challenge, before we were in the era of precision cosmology that we're in now, people wanted to know one cosmological number above all others, which was the Hubble constant, the expansion rate of the universe locally. And people have devised many methods for measuring this, and we thought we had it pretty well nailed down. This was one of the driving goals of the Hubble Space Telescope, and one of the Hubble key projects was measuring the Hubble constant. Planck came to a different answer about what the Hubble constant is.
Wow. And rewinding that, I mean, it was a phenomenal amount of work to get it to a little better than 10% a few decades ago.
Yeah, that's right. I mean, until a couple decades ago, there was a continuous argument about a factor of 2 difference in the Hubble constant. And fortunately, the number settled right between the two numbers that had been argued about, so I guess everyone wins. But yeah, so we thought we had this number to 5% roughly, and then it jumped by 6%. So that was a bit of a surprise. One thing that you can do with clusters of galaxies, with a technique that I used to find them, is actually measure the Hubble constant by using them as standard rulers. what is the shortest path from me to explaining this.
St. John's Soldovich effect. Yeah.
That's right. We've got a lot of things wrapped up in here. Okay, let's see. You guys have a couple hours, right?
Yeah.
So, how do I find galaxy clusters? Let's try and do this. Galaxy clusters are big collections of matter, so they're the largest structures in the universe, as I said before. Mostly dark matter, but 15% of them is baryons. Almost all of those baryons are not in stars like we would expect. They're in very hot gas that we only see in the X-rays. You have a bunch of hot gas sitting in a potential well. You have the cosmic microwave background coming towards you, and it's got to get to you, it's got to pass through this cluster of galaxies. About 1% of the photons in the cosmic microwave background will bounce off of the electrons in this very hot gas in the galaxy cluster. When they do this, on average, they gain energy. So you take this very perfect blackbody spectrum of the cosmic microwave background, and 1% of the photons in it, roughly speaking, get hit by electrons and gain energy. So you move photons around in that spectrum. So below the peak of the spectrum, you lose photons, and above the peak, you gain them. So if you look at the cosmic microwave background in the direction of a cluster of galaxies, you'll see, if you're looking at longer wavelengths below the peak of the spectrum, you'll see a hole in the sky. The cosmic microwave background has a hole in it, about the size of a galaxy cluster. And it turns out that no matter how far away that galaxy cluster is, because this scattering depends basically on just the temperature of the gas and the density of the gas, so the total pressure of the gas, it's proportional to the mass of the cluster. So you can find clusters of the same mass at any redshift, so throughout the whole history of the universe. So, okay, this is how we find
and that's a big benefit, because if you're just trying to find regular galaxies with increasing distance, it gets hard very quickly.
Right. So yeah, so normally things we look at in astronomy get much, much dimmer as you go to high redshift. Usually things that are not just point sources on the sky will dim like 1 plus the redshift to the fourth power. It's very, very quick loss. So you go to redshift 1 and you're 2 to the fourth power dimmer. So
and as an aside, in case anyone ever doubted it, the effect you're talking about, of course, is a proof that the CMB photons are a cosmic signal, not some local thing that's fooling us somehow.
Yeah, no, that's right. They have to be a background to these galaxy clusters. We can see the galaxies. We can see their redshift. They're clearly far away, and in fact, we're even working on a paper right now. This has been done a little bit before, but we're doing it a little better now, where you can use the galaxy clusters to measure the temperature of the CMB as a function of redshift. We think we understand how radiation should cool as you expand the universe. It's very simple, but there are ways that people have thought of to tweak the universe that the CMB could change its temperature with redshift in a different way than the very simple expectation. And so you can use these clusters to actually measure the change in the temperature of the CMB as you get further away, and confirm that in fact at redshift 2 it was 1 plus C, so 3 times hotter.
So another very fundamental test of the Big Bang picture.
That's right. Is the universe as simple as we think? It seems to be. So anyway, back to the Hubble constant. We have galaxy clusters. We find them through their hot gas. This technique I'm using is called the Sunyaev-Zeldovich effect for its thinker-uppers. And it basically measures the temperature of the gas times the density of the cluster times the size of the cluster along the line of sight. If you look in the X-ray, you measure something that's like the density of the cluster squared times the size through the cluster. So if you have the two measurements, you compare them, they differ by a power of the density, or if you square them, then they differ by a length through the cluster. So you measure the length through the cluster by comparing X-ray and SZ, and you measure the length on the sky, and you know the redshift of the cluster. And by comparing these things, you can measure the Hubble constant. And people stopped doing this several years ago. The last real measurement, real careful attempt at this was 2006. But suddenly, it's far more interesting to use another independent way to measure the Hubble constant.
Because it's worth remembering that the key project that you were talking about, it was really measuring the local universe where matter is fairly inhomogeneous. I mean, it was working out to scales where there's still large variations in the density of galaxies and so on. You're talking about a cosmic, imprint of the expansion rate on a truly cosmic scale.
Yeah, I mean, the CMB itself, obviously because Planck has some measurement of it, gives you a very, very, very large scale measurement. So all the way over the averaged out to between here and redshift of 1,000. And then the Key project. You're on the Key project team, right?
No,
never
okay.
was. Well, okay. The Key project, much more local, and people have pushed much further away with things like supernovae, and people can actually make interesting geometric measurements to larger scales with radio telescopes and very high angular resolution measurements through some technique called very long baseline interferometry. But basically, as with everything in astronomy, it's much better if we can measure it in several different ways, because there's goofiness to every individual way, and we hope that the goofiness is orthogonal between the measurements, so they sort of average out to the right answer.
I think that's a memorable phrase now, orthogonal goofiness, so I'm going to remember that one. Last topic I wanted to ask you about, which is I know a strong interest of yours, and it's very exciting, of course, is the refinement of our understanding of the supermassive black hole at the galactic center and what we can expect in the future on that. Do you want to talk a little about that?
Sure. So I've jumped around to a few different science topics talking here, but also in my career in astronomy. Generally to things that I find intriguing. So black holes are a pretty intriguing thing, right? And we have, we know there's a black hole in roughly every galaxy. This is a thing that's been confirmed over the time I've been in astronomy, and you're definitely on that team.
Yeah.
And there's of course one in our galaxy, and the amazing thing is that the one in our galaxy is very weird. It's very faint. It's eating almost nothing, and if it were in any other galaxy, we wouldn't be able to see it because it would be too faint if it were further away. Because it's in our galaxy, we can see it in great detail, and because it's not eating very much, we can basically see all the way down to the event horizon. If it were eating more, the glowing gas falling into it would obscure our view, again, like trying to look into the sun. But we're lucky. Our black hole gives us a clear view, should give us a clear view down to its event horizon. It's pretty well.
What kind of a scale are we talking about there?
So the event horizon size. So the black hole in the center of our galaxy weighs as much as 4 million suns. Interestingly, because it's so faint, it's glowing with a luminosity of about 300 suns.
Wow.
So less than many stars in our galaxy, even though it's got a mass of 4 million suns. And this is completely atypical. So if the sun were a black hole, its radius, its Schwarzschild radius, would be 3 kilometers. So at 4 million suns, it's just proportional to the mass. So it's 12 million kilometers. This is at the distance of the galactic center, so 25,000 light years away, or 8.5 kiloparsecs. This is this radius is about 10 microarcseconds, so millionths of an arcsecond. So, the highest resolution optical images are, with adaptive optics, are, tens of milli-arcsecond resolution.
Your orders of magnitude away.
Yeah, so
right?
we got to go 3 orders of magnitude beyond what we do with the best optical telescopes. I think we all pretty well accept that there are black holes in the universe. They're very common.
And the evidence for this one's probably as good or better than for any black hole,
That's
including
right.
the stellar mass black holes in the solar neighborhood.
Yeah, I mean, for this one, we can watch stars go around a dark patch on the sky. Then we can, measure their orbits in 3 dimensions because it's nearby and because we can see very close to it. The time scale for these stars to go around is 15 or 16 years for the shortest orbit. So we've actually seen complete orbits of these stars.
Which is a nice physics coincidence to match to a human lifetime.
Yeah, we probably could have done this calculation if they were a factor of several longer, but it's amazing that we've actually seen these things go around, and we're watching them go around again, and over time we can actually watch their orbits shift and infer some things about general relativity from that. But so because we can measure these orbits just like we can weigh the solar system this way, we can weigh the black hole. We know they're going around something. We don't really see it most of the time, at least in the infrared. We've weighed them. We've weighed it. We know very precisely that there's something there, and it has to be at much higher density than basically anything else could be. So there really ought to be a black hole there. Very, very strong evidence, as Chris says. But for as accepted as the black hole idea is, we've never actually seen one. I mean, we've seen the light from gas, being expelled by it as it falls in, or falling all the way in and heating up and glowing. We'd really like to take a picture of one of these things. See the material glowing as it's falling in. See the structure that material is being funneled into the black hole. See the light being warped by the very strong gravity around the black hole. But to take such a picture, as we just discussed, we need to have resolution that's 1,000 times better than anything we've ever done. So how do we do this? Well, the angular resolution of a telescope is just given by the wavelength divided by the size of the telescope. And if you want to do this, you want 10 microarcsecond resolution. You say, well, we'll observe at about a millimeter, because a wavelength of millimeters is convenient because of a technique it makes available to us. What size telescope we need? Well, we need a telescope about the size of the Earth. Obviously, that's not something we're going to build anytime soon. What we can do in the radio is we can take telescopes all over the Earth, and we can combine them as a single, very sparsely sampled telescope through a technique that I already mentioned called very long baseline interferometry, VLBI. Basically, at each telescope on the Earth, we record the electric field on the surface of the telescope, the incident radiation from each telescope. We record that very fast in great detail with very precise clocks to make sure that we're measuring exactly, we know exactly what time difference there is between each telescope when we're recording. We take all of that data and we bring it to the same place. And we feed it into a supercomputer that's specifically designed for this operation, and the supercomputer looks for the arrival of the same light at each pair of telescopes. There's going to be some time difference because there are different places on the Earth. They're closer or further to the black hole. The Earth's rotating, things like that, but it's all geometry. We can work that out. And when we can find the same light hitting the two telescopes, we can actually recreate we simulate a telescope that is as big as the separation of those two telescopes. So by doing this, we can actually achieve this 10 microarcsecond resolution.
And then as a side, the VLBI is a mature technique, but it's centimeter wavelengths. Why is this harder to do at order of magnitude longer wavelengths?
Shorter wavelength.
Shorter wavelength.
At higher frequency.
Right.
So the trick is that we have to have the biggest problem. There have been two. Number one is sensitivity. So as you get to shorter and shorter wavelengths, higher and higher frequencies, radio receivers create more and more noise of their own,
Mm-hmm.
and so the signal from the sky gets weaker compared to the noise from the telescope.
Mm-hmm.
And so you have to beat that. And people have actually improved the high-frequency radio detectors by, a factor of several in the last 10, 15 years. So this makes a big difference.
Mm-hmm.
Electronics allow us to improve this a bit further, because a radio telescope gets more sensitive if you can record a larger frequency range at one time.
Mm-hmm.
So Moore's law is helping us here. It's as simple as that. We can process more frequency at the same time because we have better computers. But the other problem was that was getting a very good clock. So the fundamental clock that we use is something called a hydrogen maser, and it uses a fundamental transition that's just the physics of the hydrogen atom, basically the change between two states of an electron in the hydrogen atom, and it produces a signal that starts at about a frequency of about 1 megahertz. We generate a signal of 5 megahertz from this fundamental atomic transition. When you want to observe at higher frequency, as you scale it up, the noise in that clock goes up like the frequency ratio squared. So when you're going to, say, 10 gigahertz, that's fine. But if you go to 100 or 200 gigahertz, then you're going 10 squared or 20 squared times worse noise. And the clock noise was actually a limiting factor. If we can't track the two telescope timing as perfectly as we need to, we don't see the same wavefront hitting the two telescopes.
Mm-hmm.
So that problem's been fixed over the last decade as well. So by getting better detectors and better electronics and fixing clocks, getting better clocks cheaper, it's now become possible to do this at very high frequency.
So these are big technical challenges that have to be solved, but let's imagine, because I think they are under control. When are we going to get these amazing pictures of the galactic center?
We're getting close. We've done a lot already. So we've made measurements with sort of 40 microarc second resolution. We found that the black hole is about the right size, so good. Everything's hanging together so far. We're clearly seeing down to the size, roughly the size of the event horizon. It turns out that you might imagine that if the radius is 10 microarc seconds, that the diameter of this thing would be 20 microarc seconds. But general relativity is weird, and so you're wrong. So the light from the black hole actually bends itself. It lenses itself. So it appears, instead of 20 microarc seconds in size, it appears about 50 microarc seconds in size. So this is the size we want to resolve. We're just sort of at that limit. The thing that's going to make it work over the next couple of years is we add a huge radio telescope array in Chile that is just being completed now. It's called ALMA. Mm-hmm. Before, we've been playing with sort of one 10-meter telescope in Arizona with a couple 10-meter telescopes in California and stuff like that. ALMA is 50 12-meter telescopes. So this is a very sensitive instrument to add into the array. And then to get the very highest resolution we can, we want to use the whole disk of the Earth. So adding ALMA helps because Chile is about halfway down the Earth as seen from the galactic center. To go the rest of the way, we go to the South Pole, and so we're building a receiver here to go to the South Pole to use a telescope there. And that'll deploy at the end of 2014. ALMA will join the array at the end of 2014. And so in the experiment in 2015, we really hope, if everything comes off, to be taking these pictures in sort of, spring of 2015. So it's
Wow.
not that far off.
That's really exciting. And amongst many things, these are new tests of general relativity, real evidence that event horizon exists, which is just a mathematical concept, really.
That's right, absolutely. We should actually be able to see, the dark, there's no light escaping in this direction, and over here on the edge we can see the light being lensed around the black hole, and it should be pretty amazing.
Right. Well, that's a great place to stop. Thanks very much, Dan.